Today we're going to be discussing the concepts of viscous drag and buoyancy force. We're going to be going over a problem that's very similar to one of your Connect problems, so if you have any trouble with this at all, please keep watching. An air bubble is rising through water at terminal constant speed of 2.75 centimeters per second. What is the terminal speed of an aluminum sphere? Specific gravity equals 2.7, with the same radius falling through water. Assume viscous drag in both cases and ignore the possibility of changes in size or shape of the air bubble. Density of air at 20 degrees Celsius is 1.2 kilogram per meter cubed, and that of water is 998.21 kilograms per meter cubed. So let's first make a key because a key will help us stay more organized for our problem because there are a lot of variables involved in this. So let's set V equal to the volume, and we know that the volume is equal for both the sphere and the bubble because we know that the R is equal. Let's set VB equal to velocity of the air bubble. Let's set VA equal to the velocity of the aluminum sphere. Let's set rho W equal to the density of the water that the air bubble and the aluminum sphere is falling through. And let's say rho aluminum, so rho Al, equal to the density of the aluminum sphere. And finally, let's set rho air equal to the density of our air bubble. So it's best to start off drawing a force diagram. And so for this air bubble, we know that there's a force of buoyancy that's going to be pointing upwards. We also know that there's going to be a force of gravity, which is due to the weight of this object pointing downwards. And because we know that this air bubble is floating upwards, we also know that there's a viscous drag force that's going to be pointing downwards as well. And so what's the relationship between these three forces? Well, we know that ultimately this bubble is floating at constant terminal velocity, meaning that the net force is equal to 0. This also means that the magnitude of the force buoyant must equal to the magnitude of the gravity force and the viscous drag force. And so a reminder about viscous drag force. So viscous drag is kind of like friction, as in it always opposes the movement of the object. So in this case, our air bubble is going to be moving upwards, so that's why we know that the viscous drag must be opposing this upward movement and be pointing downwards. So now let's evaluate our forces. So the gravity force should equal to the density of the medium, so in this case air, times gravity times volume. Our buoyant force should equal to the density of the medium that the air bubble is in, which is water, times gravity times the volume of water that is displaced. And finally, our drag force is equal to the equation on your equation sheet, which is 6 pi times the viscosity constant times the radius of the bubble times the terminal speed of the bubble. And now let's plug in these equations into our original equation, which is buoyancy force is equal to the magnitude of the gravity force plus the magnitude of the drag force. Now let's move on to scenario number 2. In the second scenario, we're going to be talking about an aluminum sphere that's falling down through the water. This is different from the air bubble because the air bubble was rising up. So there is the force due to gravity pointing downwards. There's also a buoyant force that is pointing upwards. And in this case, our drag force is going to be pointing upwards because we know that the aluminum sphere is falling down. So in order to oppose it, the viscous drag is going to be pointing upwards. And like before, because it's at constant terminal velocity, the net force is equal to 0. And so the magnitude of the force due to gravity is equal to the magnitude of the buoyant force plus the magnitude of the drag force. Let's break each of these forces down. So we know that the force due to gravity is equal to the density of the object, which is the aluminum, multiplied by gravity and the volume of the aluminum sphere. The buoyant force is equal to the density of the medium that the aluminum sphere is falling through, which is water, times gravity, times the volume of the water displaced, which is also just the volume of the aluminum sphere. Finally, the viscous drag force is equal to 6 pi times the viscosity constant multiplied by the radius of the aluminum sphere multiplied by the final terminal velocity of the aluminum sphere. Let's once again substitute these equations into our original formula. Okay, so we have two equations now, the one in the green and the one in the blue. I'm just going to rewrite these two equations down below here. Well, upon first impression, these two equations look pretty daunting and pretty scary looking. So, in order to simplify this and make this a little bit easier, let's set this 6 pi viscosity constant times radius into another constant, and let's call this constant alpha. Ultimately, we are trying to figure out what the final terminal velocity of the aluminum sphere is. And so, let's solve for the velocity for both of these two equations. So in the first equation, we're solving for the velocity of the air bubble, and the second equation, we're solving for the velocity of the aluminum sphere. Okay, now let's look at these two equations. We have two unknowns. We don't know what the velocity of the aluminum sphere is, and we don't know what alpha is. So what do? Let's divide these two equations to cancel out the alphas and get a ratio between the velocity of the air bubble and the velocity of the aluminum sphere. Judging by the look of this equation, we can cancel out the gravity constant in the denominator and the numerator. We can also cancel out the volume and the alpha constant because we are told from the very start that the radius of the aluminum sphere and the radius of the bubble are the same. After canceling out these constants, let's rewrite our equation. And so we get that the velocity of the air bubble over the velocity of the aluminum sphere is equal to the density of water minus density of air over the density of the aluminum minus the density of water. Okay, let's go back to the initial problem and figure out what the velocity of the air bubble was, what the specific gravity of the aluminum sphere was, what the density of air is, and what the density of water is. We know that the terminal velocity of the air bubble is 2.45 centimeters per second. We know that the density of water is 998.21 kilograms per meter cubed. We know that the density of air is 1.2 kilogram per meter cubed. Once again, we know what the density of water is, and we're given that the specific gravity of the aluminum sphere is 2.7. Specific gravity is used to define the density of an object compared to the density of water. So the density of aluminum would just be 2.7 times 998.21 kilograms per meter cubed. Finally, let's solve for the terminal velocity of the aluminum sphere. We get, after substituting these numbers in, that the velocity of the aluminum sphere is 4.70 centimeters per second. I hope you all found this video to both be helpful and enjoyable. If you have any more questions, please come to the Learning Center so we can assist you further.